Hello learners, welcome to Dr. D.Y. Patel Vidyapeeth's Center for Online Learning. I am Professor Dattatray Katore and I am going to teach you statistics and quantitative techniques. So in this particular unit, we are going to discuss arranging data to convey meaning, presenting data in tables and charts. So this is the first unit of your course Statistics and Quantitative Techniques. Outline of today's session. So in this unit or session we are going to discuss the meaning of statistics, collecting data, classification of data, data analysis, frequency distribution, frequency table, frequency graphs and data presentation using various diagrams. Starting with the meaning of statistics, so there are some definitions which we are going to go through. The first definition is given by Bowley. Statistics are numerical statements of facts in any department of inquiry placed in relation to each other. So this is the definition given by Bowley. Harlow defines statistics as the science and art of handling aggregates of facts, organizing enumeration, recording, classification and otherwise systematically treating them. And finally one definition is given by Croxton and Cowden. It is a very important definition for us and it is very easy to understand for a layman also. Statistics may be defined as the science of collection, presentation, analysis and interpretation of the numerical data. So we should focus on 4 points in this particular definition, that collection, presentation, analysis and interpretation. So data is collected, then the data is presented in various diagram, charts and tables, then some analysis is done and finally the interpretation is done. So these are the 4 important stages in the data processing which we are going to discuss in this particular unit. So collection of the data, presentation of the collected data, then analyzing the data which has been presented or summarized, and then drawing some useful interpretations from the analyzed data. So that is what statistics is. Statistics is an art as well as science that deals with collection, analysis, interpretation and presentation of the numerical data, which we have already discussed. Statistics is broadly classified into 2 disciplines, descriptive statistics and inferential statistics. Descriptive statistics deals with organizing and summarizing the raw data which has been collected, and inferential statistics deals with drawing useful inferences based upon the summarized and organized data. So this is the basic difference between descriptive statistics and inferential statistics. Descriptive statistics focuses on organizing and summarizing the data in the form of various tables, charts, then finding out some descriptive features of the data, and then inferential statistics deals with drawing inferences based upon the data which has been collected and organized and summarized. Types of data. So basically there are 2 types of data based upon the source. The data which has been collected for the first time, that is the fresh data or the first hand data we can call it. So such a data is called as primary data. So the data which has been collected for a specific purpose for the first time, so such kind of data is called as primary data. The data used in investigations which have already been collected by somebody else are known as secondary data. So the primary data becomes secondary when we use it for the second time, right? So the data which we use based upon some sources, based upon some data which has already been collected, then such a data is called as secondary data. For example, data relating to national income collected by the government are primary data. So every year government collect the data regarding the national income. So government collected for the first time, and it is a fresh data or first hand data, and therefore it is a primary data. But the same data will be secondary when we use it for some other purposes or different concerns. Primary data, the examples are like Reserve Bank of India's bulletin which is published monthly, Jute bulletin is published by Government of India monthly, Indian Textile bulletin is published monthly, and statement of railway board, which is published yearly published by Minister of Railways, Government of India. So these are some reports which are based upon primary data. The secondary data examples are like statistical abstract of Indian Union. Now the word abstract itself means that the information or the data has been abstracted from some other source. Abstracted means taken out or taken away from some other source, right? So it is a second hand data. So statistical abstract of the Indian Union, monthly abstract of statistics, monthly statistical digest, international labor bulletin. So these are all examples of secondary data. Methods of primary data collection: direct observation, personal interview and surveys. These are the methods to collect the primary data. So direct observing the things, persons, object, we can collect data. We can conduct personal interviews also to collect the data, or we can conduct surveys also. The various instruments which are used for the collection of primary data includes questionnaire and Google Forms nowadays we use. Methods of secondary data collection: so official publications by the central and state government and district board. Reports and committees and commissions published by publications by research institutions and universities, economic and commercial journals, publications of trade association, chambers of commerce, market reports, individual research work of statistician. So these are all examples of secondary data. Data analysis key terms: data are the actual values of a variable. So they may be numbers or they may be words. So data are basically actual values of a variable. Variable is something which can assume any value, whose value keeps on changing. So data are the actual values of a variable. They may be numbers or they may be words, and datum is a singular form of the data. Data is a plural form. Information. Now the meaningful data is called as information. Data and information. Though we tend to use data and information interchangeably in common conversations, we need to think of them as different things when we deal with statistics. Data is the raw numbers before we do anything with them. So data is unprocessed data, raw facts we can call it. So raw facts which have not yet been processed or analyzed. We haven't done any processing, statistical processing on the raw facts. Such raw facts are called as data. Then information. Information is the product of processing of data. So when we process the data in order to draw some meaningful conclusions, then the data becomes information. So meaningful data is information and raw facts are data. Again, data and information continued. Listing of scores of all the students that they have earned in business mathematics subject is data. Summary of the scores showing mean scores, then their average score we can call, by producing a table showing how many students who got A grade, how many students got B grade, etc. You have converted data into meaningful piece of information. So the first point is that the listing of scores of students who have got some marks in their business mathematics course will be your raw fact and therefore data. And when we process this data in order to calculate the average marks, then you prepare a table to show how many students who got A grade or B grade, etc. Then simply you have processed the data, and the processed data is called as information. So raw data is of no use for the decision making purpose, and hence data need to be summarized into meaningful piece of information to draw conclusions and make decisions. Population is the totality of objects under observation, the total number of objects, person, things, places, etc. undertaken in a study. The numerical value or statistical measure that describe the population is called as population parameter. So in the field of any statistical inquiry, there may be persons, items or any other similar units. The aggregate of all such units is called as universe or population. So population may be finite or infinite. So population is something what we want to study, right? Population. right? So totality of the object, so totality of the object, things, places which are under consideration of our study becomes our population or universe, and the statistical attributes or measures of the population, for example mean, median, mode, so these are called as parameters of the population. The population can be finite or infinite. So if the number of members in the population are finite, countable, then we call it finite population, otherwise infinite population. Sample. Now when the population is infinite, or when the number of elements or members or places in the population are infinite or very large, then it is very difficult to observe or collect information about each and every member in the population. So if the population consists of infinite or very large number of members, then it is very difficult to observe each and every element in that particular population. It is economically not feasible many times. It may take large amount of time, and therefore what we do, instead of studying each and every member in the population, what we do, we collect representative small portions of the entire population, and these representative small portions of the entire population are called as samples. So this is our population, this is population, and these are samples. So instead of studying entire population, we study samples, and based upon the sample we try to study the population. So as we have discussed or seen in the previous slide, that the statistical measures of the population are called as parameters. So and statistical measures or attributes of sample are called as statistics, not the subject statistic. It is statistics in plural, the statistical measure of a sample. Then statistic, it is in plural form, it can be written as statistic in the singular form, right? So statistical attribute or measure of sample are called as statistics in plural, statistic in singular, and statistical attributes or measures of population are called as parameters. So when we try to study the population, we try to study the statistical attributes of the population, but many times it is difficult to study the entire population. Therefore we collect small portions of the entire population, and on the basis of the statistical attributes of the sample, that is statistic, we try to judge the values of the parameter, which is a statistical attribute of the population, and the process is called as estimation. So the process of finding out or inferring the value of the population parameters based upon the sample statistics is called as estimation. Data analysis is continued. Variable. So variable is an attribute which can be measured or counted and can assume any value. So variable is an attribute whose values keeps on changing. There are two types of variable: discrete variable and continuous variable. So if a variable can take on any value between two specified limits, it is called as a continuous variable, otherwise it is called as a discrete variable. So we have an example here. Suppose the fire department mandates that all the firefighters must weigh between 150 to 250 pounds. The weight of a firefighter would be an example of continuous variable. So weight of a firefighter can be any number between 150 to 250. So we are defining this attribute or this variable over a range instead of a particular value. So it can be any number like 155.2, 157.6, like this, right? So this variable is called as continuous variable. We define it over a range. Then suppose we flip a coin, we toss a coin and count the number of heads. The number of heads could be any integer value between 0 plus infinity. Suppose I toss a coin 3 number of times, so there can be 0 head or 2 head or 1 head or 3 heads, right? So there cannot be 2.5 heads. So we could not, for example, get 2.5 heads, and therefore the number of heads, it can be either 0, 1, 2 or 3 when I toss 3 coins simultaneously or one after another. then this is assuming some integer values, and that's why it is a discrete variable. It is data classification. Data classification is the process of arranging data into different classes or groups according to the resemblance and similarities. An ideal classification should be unambiguous, stable, and flexible. So data classification is arranging data into different classes according to their similarities and resemblances. There are two types of classification depending upon the nature of the data. Classification according to attribute, if the data is of descriptive nature having several qualifications. So attributes like male or female, literate or illiterate. So these kind of attributes we use for the classification. This is called as classification according to attribute. Then there can be classification of numerical data in the form of class interval, so which we are going to discuss shortly. So suppose there are variables like heights and weights which assume values over a range. So these kind of variables are classified according to class intervals. So this type, the interval type of classification arises when direct measurement of data is possible. Data relating to height, weight, production, etc. comes under this category. For instance, persons having weight say 100 to 110 kgs can form one group. So this particular group is having weight or height between 110 to 120 kgs, right? So all the people will be all the people having weight between 110 to 120 kgs will be enumerated in this particular group. So we are grouping the people according to resemblances or similarities. So in this way data are divided into different classes, each of which is known as class interval. So this is called as class interval. The number of items, so how many people are there whose weight is between 110 to 120 kgs, will be the class frequency, which is denoted by the letter F. The first number of the class interval, so if this is the class interval, the first number of the class interval is called as lower limit, and the second number in the class interval is called as, this is lower limit, and the second number is called as upper limit. The difference between the limits of class interval is known as magnitude of the class or class width, or class interval we can call it. So suppose when we talk about a class 110 to 120 kgs, right, 110 kg to 120 kgs. So the difference between upper limit and lower limit, so 120 minus 110, so this is equal to 10. So this is called as magnitude of the class. The difference between the limits of the class interval is called as magnitude or class width. If for each class interval the frequencies given are aggregate of the preceding frequencies. Frequency is the number of people or number of objects that fall within the class interval or class, this particular group. So the aggregate of preceding frequencies is known as cumulative frequency. So when we go on adding the frequencies of previous classes up to that particular class, this becomes cumulative frequencies. Cumulative frequencies are of two types, less than cumulative frequency and greater than cumulative frequency. So when we go on adding the frequencies of the preceding class from top to bottom, we get less than cumulative frequency, and when we go on adding the frequencies of the preceding class from bottom to top in a frequency table, it is called as greater than cumulative frequency or more than cumulative frequency. Data classification. So class intervals are of two types, exclusive type of classes and inclusive type of classes. So the class intervals such as 100 to 110, 110 to 120, 120 to 130 are called as exclusive type of classes. Why? Because if suppose we have a number like 110 which we have to classify into these classes, so where would there is always a question that where would we classify the number 110, whether to include it in a class 100 to 110 or in a class 110 to 120, because 110 is there in both the class intervals. So what we do, we include 110 in a class where it forms the lower limit. So the upper limit is excluded from the class interval, and therefore we call it exclusive type of classes. Now again the class intervals may be in the form of 100 to 109, 110 to 119 and so on. So these kind of classes are called as inclusive type of classes, where both the limits, upper limit as well as lower limit, are included in a class interval. Here in the above case, this particular number 110. So in exclusive type of classes like this, the upper limit is not included, right? So both the limits are not included, therefore it is exclusive. And here both the limits, upper limit as well as lower limit, both are included in a class interval, and therefore it is called as inclusive type of class. Classification, frequency distribution. So after collecting data, the first task for a researcher is to organize or simplify the data so that it is possible to get a general overview of the thoughts. So this is a goal of descriptive statistical techniques. So one method of simplifying and organizing data is to construct a frequency distribution. So after collecting data, the first task for every researcher is to organize and simply summarize the data so that it is possible to get a general overview of the results. So this is goal of the descriptive statistical techniques. So one method of simplifying and organizing data is to construct a frequency distribution. So a frequency distribution continued. A frequency distribution is an organized tabulation showing exactly how many individuals are located in each category. So it is about finding out how many members, individuals, objects are located or placed in each category on a scale measurement. Frequency distribution presents an organized picture of the entire set of scores, and it shows where each individual is located relative to the other in the distribution. Frequency distribution continued. A frequency distribution table consists of at least two columns, one listing the categories. So in a frequency distribution table, we'll have at least two columns. In the first column there will be some variable like x, and in the second column the number of objects that appear or that represent that variable. So in column x, in the x column, values are listed from the highest to lowest without skipping anything. So we list the values here. And for the frequency column, for f column, tallies are determined for each value. So how many members of each values are there, how many members of each values are there. So the number of occurrences of each value is the frequency. The sum of frequency is equal to n. So n is equal to addition of all the frequencies. Frequency distribution is the organization of raw data in the table form using classes and class frequencies. So two types of frequency distribution is there: categorical frequency distribution and grouped frequency distribution. Categorical frequency distribution and grouped frequency distribution. So categorical frequency distribution is used for the data that can be placed in specific categories like normal or ordinal level data, and group frequency distribution is used when the range of data is very large. Data is grouped into classes that are more than 1 unit in width. So categorical means ungrouped, and grouped frequency means grouping of data in the form of class interval. So when the data is the number of data or number of objects in a data are very small, then we use categorical or ungrouped frequency distribution. And when the range of data is very large, the number of observations are very large, in that case we use grouped frequency distribution. So we have an example here. So this is an example of categorical frequency distribution. So 25 army indicates were given a blood test to determine their blood type. So 25 army indicates were given a blood test. So this is the result, right? So A, B, B, A, B, O. So this is the result. So we have classes here. So we have only 4 types of blood groups. So we have only 4 classes here: A, B, O, and AB. Right. So then we have tally marks here. So tally marks are optional. So the two compulsory tables that they must be there in the frequency distribution are class and frequency, or value and frequency. So A, B, O, and AB, these are the only 4 types of blood groups we know. So tally marks. So 25 peoples were observed. So this is the observation on the right hand side. This is the observation. All right. So we have A, B, B, A, B, O. So these are the observations. So how many A's are there? 1, 2, 3, 4 and 5. So here it is 5. So 5 tally marks are there, 1 for each. 1, 2, 3, 4 and 5. So for every tick you can have a tally mark. So similarly here we have a group of 5. So 5 tally marks are there. So the frequency is 5. So how many A's are there in this particular observation? 5 A's are there. How many B's are there? 7 B's are there. Now you can find it out. Then how many O's are there? 9 O's are there. How many B's, AB's are there? 4 AB's are there. So you can find it out from this particular template. So this is the frequency. Frequency is the number of occurrences. So there are 5 rows in this particular data. There are 5 rows and 5 columns, right? Therefore the data is about 25 people, right? So 25 is the total number of frequency. So when we add all the frequencies 5, 7, 9 and 4, we get 25 because this data is regarding 25 people, right? Then we can calculate the percentage frequency. So 5 divided by total frequency. So individual frequency divided by total frequency multiplied by 100 will give you total frequency. So 5 divided by 25 is 1/5. 1/5 multiplied by 100 is 20. So similarly you can calculate percentage frequency for every class. So this is categorical frequency distribution. So we haven't formed the class intervals here because the data set is small, the range is smaller. Only 4 types of data were there, right? Then organizing data. So again we have data collected in original form is called as raw data. So here we have scores and frequencies. So people with 8 score, there are 3 people. People with, okay, the raw data is mentioned here on the right hand side. Let me take the pointer. So this is the raw data, right? How many observations are there? 1, 2, 3, 4, 5, 6, 6 3s are 18, right? So these 18 observation raw data is given to us and we have to arrange it in the form of frequency distribution. Now this is again categorical frequency distribution or ungrouped frequency distribution because we have here scores, right? How many, what is the range, what is the largest number in this particular raw data? The largest number is 8 and what is the smallest number? 2. So range is only 6, 8 minus 2, which is a range. So range is very small. So we can have 6 classes, 1, 2, 3, 4, 5, 6 values only, right? And therefore how many 8s are there in the raw data? 3 8s are there, like 1, 2 and 3 8s are there. How many 7s are there? 2 7s are there, 2, right? So similarly we can write down the frequency for every value, right? So this is a frequency distribution table, right? So we have value. We have to take care that in while writing a frequency distribution table, in the value column we should not repeat any value, right? Otherwise it will not satisfy the purpose of summarizing the data, tabulating the data. So this is what score is and the frequency distribution table. This is categorical data. A research study has been conducted examining the number of children in the families living in a community. The following data has been collected based upon random sample of 30 families from the community. So these are the 30 numbers. Organize this data in a frequency table. So what do we do? So again we have number of children here 0 to 8. Why 0 to 8? Because the smallest number in this particular observation, there are 30 families, right? The smallest number is 0, the largest number is 8, right? So so the range is again very small, 0 to 8, only 8 values we have to write in the column 1, so 0 to 8, and again then we have to count it. How many zeros are there, how many ones are there, how many twos are there, how many threes are there. So similarly we can do that. So this is again ungrouped frequency distribution. Then we can calculate the relative frequency also from frequency, like 2 divided by the addition of all the frequency will be equal to 30 because we have observed 30 families. So 2 divided by 30, 3 divided by 30, 5 divided by 30 and so on. This is how we can find out the relative frequencies. Now construct a similar frequency table for the age of patients with heart related problems in a clinic. The following data has been collected based on a random sample of n is equal to 30 patients who went to the emergency room of the clinic for heart related problems. So the measurements are, so these are the 30 patients again, right? So let us find out the range. What is the range? So the smallest number here, let us try to find out. The smallest number here is 31, 38, then 36, 32, 32, 32, 32. So yes, 32 is the smallest number. What is the largest numbers? 72, then 72. Yes, 72 is the largest. So 32, 72 minus 32 is 40, which is a large number. So the range of this data is 40. So therefore we have a class grouped frequency distribution here. So we form groups or classes like 32 to 36, 37 to 41, 42 to 46, 47 to 51, 52 to 56. So there is a gap of 4, like the class width is 4, and then we calculated frequency. So how many people fall within this age group 32 to 36? There are 2 people. How many people fall in this group 37 to 41? There are 3 people. So similarly we find out the frequency, and the addition of frequency will give you the number of total observations, that is 30, and then we can calculate the relative frequency also. So this individual frequency divided by total frequency will give you relative frequency. So this is grouped frequency distribution. Now in a group frequency distribution we have class limits, lower class limit, upper class limit, class boundaries, upper class boundaries, lower class boundaries. So 24 to 30, this is called as class limit, this is called as class interval, and these are the class limits. Alright, so this 24 is known as lower class limit, and 30 is called as upper class limit. So this is lower limit of the class, 30 is the upper limit. 24 to 30 is the first class, then 31 to 37 is the second class, 38 to 44 is the third class, and so on. So these are the class limits. Now what is the difference between class limits and class boundaries? We have class boundaries here. Now look at the first class and the second class. The first class is 24 to 30 and the second class is 31 to 37. So there is a gap of 1 between these two classes, because the upper limit of first class is 30 and the lower limit of the second class is 31. So there is a gap. Suppose there is a number 30.5, where would you represent or write that particular number? So there is a problem. Therefore we convert the class limits into class boundaries. How do we convert? See, there is a gap of 1 between 30 and 31. Right, let me take the pointer. There is a gap of 1 between 30 and 31. So we need to distribute this gap. So how do we distribute this gap? We add 0.5 to 30 and we subtract 0.5 from 31. Right, so as we are making changes in one limit, we have to make changes in other limit also. So it becomes 23.5. So without changing the class width we have to do it, and therefore when we do when we change 30 from 30 to 30.5, we have to make changes here also, because we have to keep the class width same. So this will become 23.5. So I am writing it here. So 24 to 30 was the first class, and 31 to 37 is the second class. Now we need to convert these class limits into class boundaries. So there was a gap of 1. So we need to distribute this gap of 1 between these limits. So this we have to do. We have to add here 0.5 and we have to subtract 0.5 here from here. So it becomes 30.5. So as we are making changes here, we have to make changes here, because we have to keep the class width, the difference between upper limit and lower limit, same. So therefore as we have added here, we have to subtract here. So 23.5, and this will become 37.5. So this is how we convert the classes into class limits into class boundaries. So in this distribution the values 24 and 30, so the same explanation is given here. So in this distribution the values 24 and 30 of the class are called as class limit. 24 is the lower class limit, 30 is the upper class limit. So here it is, 24 is the lower class limit, 30 is the upper class limit. Right, the number in the second column are called as class boundaries. The class boundaries are used to separate the class so that there is no gap in the frequency distribution. So for example, I told you that if there is an observation like 37.5, where would you accommodate it? So that problem is there. Therefore we convert the class limits into class boundaries. So the class boundaries are used to separate the class so that there is no gap in the frequency distribution. Lower boundary is equal to lower limit minus 0.5, upper boundary is equal to upper limit plus 0.5. So I have shown you that calculation here also. So what we do, we add 0.5 here, therefore we subtract 0.5 from the lower limit. Class limits should have the same decimal place value as the data, but the class boundaries should have one additional place value and end in a 5. So for example, class limit is 7.8 to 8.8, class boundary would be 7.75 to 8.85. So the lower boundary is equal to lower limit. So lower limit is 7.8, here it is, minus 0.005, minus 0.05. So this will give us 7.75, and the upper boundary will be equal to upper limit. Upper limit was 8.8, so this is the upper limit plus 0.05. So this adjustment we have to do. The lower class limit represents the smallest data value that can be included in the class. The lower class limit represents the smallest data value that can be included in a class, and the upper class limit represents the largest data that can be included in a class. So 24 is the lower limit, 30 is the upper class limit. So 30 is the maximum largest value which we can accommodate in this particular class interval, and 24 is the smallest value which we can include in 24 in this particular class interval. The numbers are used to separate the classes so that there are no gaps in the frequency distribution called as class boundaries. Now here is a question, find the class boundaries for each class. So now you can find it out. So this is for your practice or homework. So you can find out the class boundaries from this class interval. Class width. So class width is found by subtracting the lower limit from the upper limit. So that is basically the difference between upper limit and lower limit. So class width is equal to lower of second class. So there are various ways to calculating it. So here it is given. So when we have class limits, we can calculate 31 minus 24. We can get the class width as 7. And when we have class boundaries, we can calculate directly, right? So when we have class limits, what we do, we take lower limit of second class. So this is the first class, this is the second class. Let me take the pointer again. This is the first class, right? This is second class. So we take lower limit of the second class, and we subtract the lower limit of the first class. So 31 minus 24, this is equal to 7. One more way to do it, when we have class boundaries, we can directly subtract the lower limit from the upper limit, right? So we need to have class boundaries for direct calculation. So 30.5 minus 23.5 will give us 7 again. So 30.5 minus 23.5 is again equal to 7. So the class width is 7. Class midpoint. So how do we find out the midpoint? It is equal to a lower boundary plus upper boundary divided by 2, or lower limit plus upper limit divided by 2. So that doesn't make any difference whether you take limits or boundaries. So these are the limits, 24 and 30. So 24 plus 30 divided by 2, this will give you 27. And when we take class boundaries, so 23.5 and 30.5 divided by 2, this will again give you 27. So that doesn't make any difference whether you take limits or class boundaries. Rules for classes in grouped frequency distribution. So these are some general rules regarding the frequency distribution. There should be 5 to 20 classes. So the class width should be an odd number. So class width should be an odd number. The classes must be mutually exclusive. Alright, mutually exclusive I told you in previous slides. Then classes must be continuous. There shouldn't be any gap. The classes must be exhaustive. All the numbers must be represented in the class frequency distribution. The classes must be in equal width. The width of the class should be equal. So this is it. So 10 to 20, 20 to 30, 30 to 40, 40 to 50, 50 to 60. So better way to construct a frequency distribution like 10 to 20, 21 to 31, 32 to 30, 32 to 42. So this is how it is done. So constructing a grouped frequency distribution, the following data represent the record high temperatures for each of the 50 states. Construct a group frequency distribution for the data using 7 classes. So we have to use 7 classes. So what is the largest number in this? The largest number is 134 and the smallest number is 100. So let me take the pointer. So 134 minus 100, this will give you 34. So 34 is the range of the data. Alright. So largest number is 134 and the smallest number is 100. Now we have to divide this range by the number of classes you have to make. So 34 divided by 7, this will be equal to 7 4s are 28 and 6 are there. So 7 9s are 63, 7 8s are 56. So this is approximately equal to 5. So we have to form the classes in such a way that class width is 5. So this is again shown in the next slide. So range we calculate, 134 was the largest number, 100 was the smallest number, range was 34. Width is equal to, width of the class interval is equal to range divided by 7. 7 is the number of classes which we have to form as given in the problem. So 34 divided by 7 gives us 4.9 and 4.9 can be rounded up to 5. So we have to form the classes taking class width is equal to 5. Alright. So this is how we can do it. So 100 to 104 class width is 5, right? How do we calculate the class width? In case of class limits, we take the lower limit of the second class and the lower limit of the first class. So this is the class width, or we can directly calculate from class boundaries the difference between the upper limit and the lower limit. Alright, so this is also equal to 5. So we have taken class width as 5 and we have started from 100 and 134 was the largest number, so 134 is here. So we can accommodate all the values now. So between 100 to 104 there is no observation, right? Then okay, it has shifted down by one place, so it should be 2 here, right? There are 2 values between 100 to 104. Let us check. So 100, right? Here we have 100. Then which is the second value? Yes, okay, 108, 9, 20. Not able to locate it now. So okay, there are 2 values. We'll consider that 2 values between 105 to, okay, 100 to 104 there are 2 values. Between 105 to 109 there are again 8 values. Similarly, we can calculate how many values fall within that particular range, respective range, and this is called as frequency. Now from frequency we can calculate the cumulative frequency also. So as already discussed, how do we calculate the cumulative frequency? So by adding the frequencies of the preceding classes we can get the cumulative frequency. So here it is 0. So 0 plus this is starting from 0 again. So 0 plus 2 is 2, 2 plus 8 is 10, 10 plus 18 is 28, 28 plus 13 is 41, 41 plus 7 is 48, 48 plus 1 is 49, 49 plus 1 is 50. So this is how you get the cumulative frequency. This is a less than cumulative frequency. There is one more variant of this which is known as more than cumulative frequency. The data shown here represent the number of miles per gallon that 30 selected 4-wheel drive sports utility vehicles obtain in city driving. So this is mileage per gallon of 30 vehicles. So we can again calculate the range. The largest value is 19, smallest value is 12, the range is 7. So the class consisting of the single data value can be used here. They are 12, 13, 14, 15, 16, 17, 18 and 19 because the range was very small, and therefore we can use the ungrouped frequency classification. So we have ungrouped frequency classification here. Alright. So this is how we can do it. So this is for you. Find the class boundaries, midpoint of the last class and the class width. So this is for your practice. So thank you for watching this video. This is the part 1 of the unit 1. We will be having one more part of this particular unit because the unit is very large and introductory, so I need to cover it in 2 parts. So this was the part 1 of this unit. and we will be discussing the rest of the part in the second session or second video. So thank you all for watching. So frequency tables we have studied in the previous part of this unit, and in this recording now we are going to study the frequency distribution graphs. So the various types of graphs which we can draw from based upon the frequency distribution table. So in a frequency distribution graph, the score categories x values are listed on the x-axis and the frequencies are listed on the y-axis. So let me show you with this pointer. So the categories values are mentioned on the x-axis. We have scores or values or variable on the x-axis, and their frequencies are mentioned. The number of occurrences of each score are mentioned on the vertical axis or y-axis frequency. So when the score categories consist of numerical scores from an interval or ratio scale, the graph should be either a histogram or polygon. So when the data source is from interval or ratio scale, we should use histogram or polygon. So there are various types of frequency distribution graphs such as histograms, frequency curve, frequency polygon, and ogives, which we are going to discuss in this particular video. For continuous data, so three most commonly used graphs in research are as follows, like histogram, polygon, and the cumulative frequency graph. Histogram. Now the histogram is a graph that displays the data by using contiguous vertical bars, or you can call it continuous, unless the frequency of a class is 0 of various heights to represent the frequency classes. The class boundaries are represented on the horizontal axis. So again I will show you with the help of graphics. So histogram is basically a graph that displays data using continuous vertical bars. So we have data using continuous vertical bars like this. There is no gap in the bars, right? There is no gap in the bars. So such kind of bars, such kind of graph is called as histogram, where we have class boundaries on x-axis. So this is x-axis, we have class boundaries, right? So this particular bar, this particular point will show the lower limit or lower boundary, and this particular point will show you the upper boundary of the class. And we have frequencies, the number of occurrences or number of elements that fall within the class boundary or class limits. So this is the example of class histogram. So in a histogram, a bar is centered above each score or class interval. So when we have ungrouped data, we don't have class interval, we have categorical classification or categorical frequency distribution. In that case we will be having a frequency, we will be having a histogram like this. So we have only values mentioned here, categorical values 1, 2, 3, 4, 5. So we don't have class boundaries or class interval here, because this is categorical frequency distribution. This is based upon the categorical frequency distribution table. So we have only categories here 1, 2, 3, 4, 5, and their frequencies are mentioned here. So the height of this histogram represent the frequency. The height is equal to frequency. For example, the category is 1, so this category appears only once and therefore its frequency is 1. Suppose the category is 3, now this category or this variable appears 4 number of times and therefore the frequency is 4. When we have grouped frequency distribution like this, then we can have then for this particular bar, the lower limit will be this particular point, upper limit or upper boundary will be this particular point, and the height will be equal to the frequency, that is the number of members in that particular group. Suppose 30 to 31 is the class 1 or the class limit class interval 1, and 2 is the frequency. Therefore 2 people or 2 members are there in this particular class interval 30 to 31. So 30 is the lower limit, 31 is the upper limit, and the frequency which is equal to height of this particular bar. So both of these are example of histogram. This particular, the diagram on the right hand side is for the categorical frequency distribution table, and the diagram which we have on the left side, bottom of left side. So this particular histogram is for class interval type of data, that is grouped frequency distribution. Construct a histogram to represent the data for the record high temperature for each of the 50 states. So we have an example here. So the same example is continued which we studied in the previous part. So class limits are given here, 100 to 104, 105 to 109. So these are the class limits which can be converted into class boundaries. Now you know how to convert the class limits into class boundaries, which we have studied in the previous part, and the frequencies are given here in the third column. So this is the example, and from this example we have to draw a histogram. So how do we draw it? So while drawing a histogram, we take coordinate axis. On x axis we take class boundaries, right? We take class boundaries here, and we take frequencies on the y axis. So frequency is equal to height of the bar. So the first class boundary is 99.5 to 104.5. So 99.5 will start from here. So 99.5. Then the second upper limit or upper boundary of this particular class interval is 104. So I write 104 here, 104.5. So we have to draw a bar of height 2 by assuming some suitable scale like this. Second boundary is 104.5 to 109.5. So the upper limit, the upper boundary of the first class interval is equal to lower boundary of the second class. So there will be continuity in the bars. So 104, and the next is 109. So I write 109 here, 109.5. and what is the frequency? Frequency is 8. So we have to draw a bar of height 8 like this. So this is how a histogram is drawn. So this is the histogram for the example which we have seen on the previous slide. Right, this is 2, this is 8. So similarly we have frequencies like 8, 18, 13, 7. So 8, 18, 13, 7, and so on. So this is how we draw the histogram. Now we should understand from histogram that when we connect the midpoints of the upper side of this every bar. So when we find out the midpoints like this, and when we connect these midpoints by a freehand curve or freehand sketch like this, the curve we get, is called as a frequency curve. So this is a frequency curve, right? So frequency curve can be drawn without histogram also. So this is by using histogram. So what we are doing, we are taking mid values, midpoints of every class. So midpoints will be like here, right? So we are taking these points and we are drawing a freehand sketch like this, and this freehand sketch is called as frequency curve. And when we connect these endpoints, or when we close these endpoints on x axis like this, the same diagram becomes a closed polygon, a frequency polygon, a closed diagram which is frequency polygon. So a histogram can be used to draw the frequency curve, and frequency curve can be converted into frequency polygon by ending these ends, closing these ends on x axis, right? Frequency polygon. So frequency polygon is a graph that displays the data by using the lines that connect points plotted for the frequencies at the midpoint of the classes. The frequencies are represented by the heights of the points. Same thing is continued. The class midpoints are represented by the horizontal axis. So basically what we do without histogram, how do we draw the frequency polygon? We take class boundaries here, right? Class boundaries. Instead of class boundaries, we take midpoints of class boundaries, right? We take midpoints and we take frequency here. So for every class, suppose we have a class boundary here. What is the midpoint of this class? How do we find it out? 104.5 plus 99.5. So this is equal to 105 plus 99, which is equal to 204, divided by 2. So upper limit, upper boundary plus lower boundary divided by 2. So this is equal to this is equal to 204 divided by 2 is 102. So 102 is the midpoint of this class. 102 is the midpoint. So we take midpoint on the x-axis while drawing frequency polygon. So we take midpoints here. We take midpoints here on the x-axis and the respective frequency on y-axis. So we take midpoints here, midpoints of class boundaries here, and frequency here. Then we take points. We can draw a curve which is called as frequency curve, and when we close the ends of the frequency curve on x-axis, we get frequency polygon. Construct a frequency polygon to represent the data for the record high temperatures for each of the 50 states. So we have class limits, so directly we can find out class midpoints without calculating the class boundaries. Also we can find class midpoints. So we have class midpoints like 102, 107, 112, 17, 22, 27, 32, and we have frequencies. So we take midpoints on the x-axis, we take frequency on the y-axis, then we take these points, we plot these points, right? For every midpoint there is a frequency. Here it is 2, then it is 8, and so on. This is 18, this is 13, 7, and so on. So this is how we plot the frequency against the midpoints, and then we draw a freehand sketch which is called as frequency curve. And when we close the ends, on x-axis, it becomes frequency polygon. Then we have cumulative frequency graphs or ogives based upon cumulative frequency. The ogive is a graph that represents the cumulative frequencies for the classes in a frequency distribution. The cumulative frequency distribution is a distribution that shows the number of data values less than or equal to a specific value. The upper class boundaries are represented on the horizontal axis. So suppose we have this example, alright, we have class limits, then we have converted the class limits into class boundaries. The same example is continued. Then we have frequencies here. Now from frequencies we can calculate the cumulative frequency. Alright, how do we calculate the cumulative frequency? So this is basically the less than cumulative frequency. So the class boundaries now will become like this, less than 99.5. So we know that there is no observation whose value is less than 99.5. So 0 here. Then what we do, we add 2 to it. So 0 plus 2 is 2, 2 plus 8 is 10, 10 plus 18 is 28, 28 plus 13 is 41, 41 plus 7 is 48. So basically we go on adding. Alright, so here I calculate it. Frequency for the first class, cumulative frequency for the first class, that is less than 99.5. So when we calculate the less than cumulative frequency, we calculate it on the lower limit. So the less than 99.5, so less than 99.5, there is no observation, so therefore it will be 0. Then it will be 0 plus 2, 0 plus 2 is 2, right? So I am writing it here, 0, 0, okay, 0, it will shift down, 0 plus 2 is 2, 2 plus 8 is 10, 10 plus 18 is 28, 28 plus 13 is 41, 41 plus 7 is 48, 48 plus 1 is 49, 49 plus 1 is 50. So this is how it is calculated. So less than cumulative frequency, it means that there are 0 observations whose value is less than 99.5. There are 2 observations having value less than 104.5. There are 10 observations having value 109.5. So we know that there are 2 observations whose value lies between 99.5 to 104.5. There are 8 observations whose value lies between 104.5 to 109.5. It means that there are 10 observations whose value is less than 109.5. So this is how we calculate the less than cumulative frequency. So we calculate less than cumulative frequency and we plot it against the lower limits of the class boundaries or lower class boundaries. So we take lower class boundaries on x-axis, lower class boundaries, that is 99.5, then 104.5, and so on, and then we take less than cumulative frequency on the y-axis, and the graph we get is the is the less than ogive. So this is less than ogive. Similarly, there is one more graph which is called as greater than ogive. So the greater than ogive will be like this, right? So this is less than ogive. Here we have a greater than ogive. So basically the midpoint of this, when we take projection from the midpoint of these ogives or intersecting point of these ogive, what we get on the x-axis is the graphical value of median. Now I will discuss here how to calculate the greater than cumulative frequency also. So let me check the eraser first. Let me erase all these values. So let us calculate the less than cumulative frequency once again. So 2 is the frequency for the class boundary 99.5 to 104.5, right? It means that there are two observations, two members or elements whose value lies between 99.5 to 104.5. There are 8 observations whose value lies between 104.5 to 109.5. So from this what we can say, there are 2 plus 8 observations are there whose value is greater than 109.5. So this is what is called as greater than cumulative frequency. So first of all, let us calculate the less than cumulative frequency. The less than cumulative frequency is plotted against the upper class boundary, and the greater than cumulative frequency is plotted against the lower class boundary. So let us first calculate the less than cumulative frequency LCF. So this will be 0 will be before this, then 2 plus 8 is 10, 10 plus 18 is 28, 28 plus 13 is 41, 41 plus 7 is 48, 48 plus 1 is 49, 49 plus 1 is 50. Now we will do it in the reverse order. Here we write down 1, we are calculating more than or greater than cumulative frequency now. So we write down 1 as it is, 1 plus 1 is 2, 2 plus this 7 is 9, 9 plus 13 is 22, 22 plus 18 is 40, 40 plus 8 is 48, 48 plus 2 is 50. So this is more than cumulative frequency. So this less than cumulative frequency has relevance to the upper class boundary, and the more than cumulative frequency has relevance to the lower class boundary, because the less than cumulative frequency represent the number of observations whose value is less than the upper class boundary, and more than cumulative frequency represent the total number of observations whose value is greater than the lower class boundary. So this is how we calculate, and when we plot the less than cumulative frequency and more than cumulative frequency on the graph, so we take these class boundaries here like 99.5, then we take 104.5, right, so on. So less than cumulative frequency is plotted against the upper class boundary, and the more than cumulative frequency or greater than cumulative frequency is plotted against the lower class boundary, and the curve we get, this is a more than cumulative frequency curve, and similar curve we get exactly contrasting this. So this is a less than cumulative frequency curve. So this is how we get, this is called as less than ogive, actually ogive, less than ogive, and this is called as more than ogive. So we get intersecting point here, and when we draw a perpendicular from this intersection point on x-axis, the value we get on x-axis is the graphical value of median. Now we will be discussing what is median in the coming session. So this is the graphical value of median. Median is a measure of central tendency. So this is how we draw less than and more than ogives. Relative frequency. So many populations are so large that it is impossible to know the exact number of individuals frequency for any specific category. In these situations, population distributions can be shown using relative frequency instead of absolute number of individual for each category. So when the, the population is so large and it is impossible to know the exact number of individuals or frequency, then instead of that we use the relative frequency to represent um, the frequency or to compare the data. So the distribution using proportion instead frequency raw data as frequencies called as relative frequencies. So we have relative frequency here on the y-axis and type of fish here on the x-axis. So bluegill and bass. So clearly from the size of the bar itself you can judge the relative strength of that particular presence of that particular fish. So bluegill and bass. So from the relative size of the bars we understand the significance or the number of observations in each category. Construct a histogram frequency polygon ogive using relative frequencies for the distribution shown here. So again we have a new example here to draw the polygons, histogram and relative frequency diagram. So we have class boundaries and frequencies given. So we can draw the histogram, we can calculate the relative frequencies. So for the data, so the following is the frequency distribution of miles run per week by 20 selected runners. So these are the class boundaries which are already given. Frequency is given, summation of frequency is 20 because this data is regarding the 20 selected runners. We can calculate the relative frequency. How do we calculate the relative frequency? Frequency divided by summation of frequency. So 1 divided by 20, 2 divided by 20, 3 divided by 20, 5 divided by 20 and so on. This is how we get the relative frequency, and the sum of all the relative frequencies is always equal to 1. So this is how we draw the histogram. So histogram is a continuous bar diagram like this. So we know how to draw the frequency polygon also from the frequency histogram also. So from histogram itself we can draw the frequency polygon by taking these midpoints and connecting these midpoints by a freehand sketch like this. So we get a frequency curve, and when we close this frequency curve on x-axis we get a frequency polygon. So frequency polygon is drawn here. Then ogives. So from the same data we can draw ogives. So class boundaries, we calculate less than cumulative frequency. So this is what ogive is. So this is less than ogive. So similarly polygons can also be drawn from the same data. Alright, so we have bar diagrams are there. So when the scores categories x values are measurement from a nominal or an ordinal scale, the graph should be a bar graph. A bar graph is just like a histogram except that gaps or spaces are left between the adjacent bars. So there is one more type of classification which is called a stem and leaf classification. So here we have some data. So we write down stem here and leaf here. So we can see here how many numbers are there starting from 30. So 33, then we have, so 33, it is only one number. So this first number, that is the 10th place, becomes stem and the units place here becomes leaf. The second number is 42. So 4 becomes stem and 2 becomes leaf. So 4 is the stem and 2 is the leaf. So similarly we can write down all these values here. So stems, like 4 is stem, 9 is leaf, 4 is stem, 9 is leaf, 5 is stem, 3 is leaf, and so on. So this kind of representation or classification is called as stem and leaf classification. So we have data here. So this is the raw data which is arranged in the form of stem and leaf classification, right? So for example, there should be number 32 and 33 here. So here it is 33 and 32 is here. So we have arranged this raw data into a stem and leaf diagram. Here it is display. Now from this also we can draw a frequency table. So what we have done, we have taken here 30 to 39, 40 to 49, and the frequency we have taken here. So how many values are there between 30 to 39? 2 values, right? So similarly here these 2 values are written here. Between 30 to 40 there are 2 values, right? So 32 and 33. Then this second bar represent 40 to 49. So from the stem 4 we have two values, two leaves, 2 and 6. So similarly we can draw the histogram for the stem and leaf diagram also. Type of data classification, stem and leaf classification. The stem plot, that is stem and leaf classification, is a quick way to graph data and give an exact picture of the data. So you want to look for an overall pattern, any outliers. An outlier is an observation of data that does not fit the rest of the data. So it is sometimes called as extreme value. So when you graph an outlier, it will appear not to fit the pattern of the graph. Some outliers are due to mistakes. So for example, writing down 50 instead of 500, while others may indicate that something unusual is happening, it takes some background information to explain outliers. So we'll cover them in more detail later. Then there are some shapes of distribution. So when we have histogram like this, the first diagram I am talking about, so this type of histogram is called as bell shaped histogram, and a bell shaped histogram means it is a normal distribution. We can get a uniform distribution like this also. So when we get a flat frequency distribution or flat histogram like this, so this is called as uniform distribution of histogram. Otherwise we can have a J-shaped histogram or reverse J-shaped histogram. Then there are shapes of distribution like skewness. So if we get a rightly skewed histogram like this, so this is also called as positively skewed histogram. We can also get a left skewed histogram. Skewness is the shape of the distribution. So this will be called as a left skewed histogram. We can have a bimodal histogram where there are two modal values. We can have a U-shaped histogram also. We will be discussing various shapes of the histogram in detail in coming sessions. Then there are some other types of graphs like bar graph is there, Pareto chart is there, the time series graph is there, the pie chart is there, which is beyond the scope of this video. So thank you so much for watching this video. I hope you must have enjoyed the video, and again thank you so much.